Section 4 of Climatic Changes, Their Nature and Causes, by Ellsworth, Huntington. This LibriVox recording is in the public domain, recorded by Leon Harvey. Chapter 4. The Solar Cyclonic Hypothesis. The progress of science is made up of a vast succession of hypotheses. The majority die in early infancy. A few live, and are for a time widely accepted. Then some new hypothesis either destroys them completely or shows that, while they contain elements of truth, they are not the whole truth. In the previous chapter we have discussed a group of hypotheses of this kind, and have tried to point out fairly their degree of truth, so far as it can yet be determined. In this chapter we shall outline still another hypothesis, the relation of which to present climatic conditions has been fully developed in Earth and Sun, while its relation to the past will be explained in the present volume. This hypothesis is not supposed to supersede the others, for so far as they are true they cannot be superseded. It merely seems to explain some of the many conditions which the other hypotheses apparently fail to explain. To suppose that it will suffer a fate more glorious than its predecessors would be presumptuous. The best that can be hoped is that after it has been pruned, enriched, and modified, it may take its place among the steps which finally lead to the goal of truth. In this chapter, the new hypothesis will be sketched in broad outline, in order that in the rest of this book, the reader may appreciate the bearing of all that is said. Details of proof and methods of work will be omitted, since they are given in Earth and Sun. For the sake of brevity and clearness, the main conclusions will be stated without the qualifications and exceptions which are fully explained in that volume. Here it will be necessary to pass quickly over points which depart radically from accepted ideas, and which therefore must arouse serious question in the minds of thoughtful readers. That, however, is a necessary consequence of the attempt which this book makes to put the problem of climate in such form that the argument can be followed by thoughtful students in any branch of knowledge and not merely by specialists. Therefore the specialist can merely be asked to withhold judgment until he has read all the evidence as given in Earth and Sun, and then to condemn only those parts which are wrong and not the whole argument. Without further explanation, let us turn to our main problem. In the realm of climatology, the most important discovery of the last generation is that variations in the weather depend on variations in the activity of the Sun's atmosphere. The work of the great astronomer Newcomb and that of the great climatologist Köppen have shown beyond question that the temperature of the Earth's surface varies in harmony with variations in the number and area of sunspots. The work of Abbott has shown that the amount of heat radiated from the Sun also varies, and that in general the variations correspond with those of the sunspots, although there are exceptions, especially when the spots are fewest. Here, however, there at once arises a puzzling paradox. The Earth certainly owes its warmth to the Sun, yet when the Sun emits the most energy, that is, when the sunspots are most numerous, the Earth's surface is coolest. Doubtless the Earth receives more heat than usual at such times, and the upper air may be warmer than usual. Here we refer only to the air at the Earth's surface. Another large group of investigators have shown that atmospheric pressure also varies in harmony with the number of sunspots. Some parts of the Earth's surface have one kind of variation at times of many sunspots, and other parts the reverse. These differences are systematic, and depend largely on whether the region in question happens to have high atmospheric pressure or low. The net result is that when sunspots are numerous, the Earth's storminess increases, and the atmosphere is thrown into commotion. This interferes with the stable planetary winds, such as the trades of low latitudes and the prevailing westerlies of higher latitudes. Instead of these regular winds, and the fair weather which they bring, there is a tendency toward frequent tropical hurricanes in the lower latitudes, and toward more frequent and severe storms of the ordinary type in the latitudes where the world's most progressive nations now live. With the change in storminess there naturally goes a change in rainfall. Not all parts of the world, however, have increased storminess and more abundant rainfall when sunspots are numerous. Some parts change in the opposite way. Thus, when the Sun's atmosphere is particularly disturbed, the contrasts between different parts of the Earth's surface are increased. For example, The northern United States and southern Canada become more stormy and rainy, as appears in Figure 2, and the same is true of the southwest and along the South Atlantic coast, in a crescent-shaped central area. However, extending from Wyoming through Missouri to Nova Scotia, the number of storms and the amount of rainfall decrease. Figure 2 is displayed on the page, storminess of sunspots maxima versus minima after Kulmer, based on 9 years nearest sunspot minima and 9 years nearest sunspot maxima in the 3 sunspot cycles from 1888 to 1918. Heavy shading indicates excess storminess when sunspots are numerous. Figures indicate the average yearly number of storms by which years of maximum sunspots exceed those of minimum sunspots. The two controlling factors of any climate are the temperature and the atmospheric pressure, for they determine the winds, the storms, and thus the rainfall. A study of the temperature seems to show that the peculiar paradox of a hot sun and a cool earth is due largely to the increased storminess during times of many sunspots. The Earth's surface is heated by the rays of the sun, but most of the rays do not in themselves heat the air as they pass through it. The air gets its heat largely from the heat absorbed by the water vapor, which is intimately mingled with its lower portions, or from the long heat waves sent out by the Earth after it has been warmed by the sun. The faster the air moves along the Earth's surface, the less it becomes heated, and the more heat it takes away. This sounds like a contradiction, but not to anyone who has tried to heat a stove in the open air. If the air is still, the stove rapidly becomes warm, and so does the air around it. If the wind is blowing, the cool air delays the heat of the stove and prevents the surface from ever becoming as hot as it would otherwise. That seems to be what happens on a large scale when sunspots are numerous. The sun actually sends to the earth more energy than usual, but the air moves with such unusual rapidity that it actually cools the earth's surface a trifle by carrying the extra heat to high levels where it is lost into space. There has been much discussion as to why storms are numerous when the sun's atmosphere is disturbed. Many investigators have supposed it was due entirely and directly to the heating of the Earth's surface by the sun. This, however, needs modification for several reasons. In the first place, recent investigations show that in a great many cases, changes in barometric pressure precede changes in temperature and apparently cause them by altering the winds and producing storms. This is the opposite of what would happen if the effect of solar heat upon the Earth's surface were the earthly agency. In the second place, if storms were due exclusively to variations in the ordinary solar radiation, which comes to the Earth as light and is converted into heat, the solar effect ought to be most pronounced when the center of the sun's visible disk is most disturbed. As a matter of fact, the storminess is notably greatest when the edges of the solar disk are most disturbed. These facts and others lead to the conclusion that some agency other than heat must also play some part in producing storminess. The search for this auxiliary agency raises many difficult questions which cannot yet be answered. On variations in the amount of ultraviolet light may also be important. Many investigators have shown that the sun emits electrons. Hale has proved that the sun, like the Earth, is magnetized. Sunspots also have magnetic fields, the strength of which is often 50 times as great as that of the sun as a whole. If electrons are sent to the Earth, they must move in curved paths, for they are deflected by the sun's magnetic field and again by the Earth's magnetic field. The solar deflection may cause their effects to be greatest when the spots are near the sun's margin. The terrestrial deflection may cause concentration of bands roughly concentric with the magnetic poles of the Earth. These conditions correspond with the known facts. Farther than this we cannot yet go. The calculations of Huntington intensifying storms. On the other hand, the peculiar way in which activity upon the margins in the other direction. Possibly the sun's electrons and its electrical vapor in the upper air. Any one of these processes would raise the temperature, but any such change in the temperature of the upper air would influence the lower air through changes in barometric pressure. These considerations are given here because the thoughtful reader is likely to inquire how solar activity can influence storminess. Moreover, at the end of this book, we shall take up certain speculative questions in which an electrical hypothesis will be employed. For the main portions of this book, it makes no difference how the sun's variations influence the Earth's atmosphere. The only Table 6 essential point is that when the solar atmosphere is active, the storminess of the Earth increases, and that is a matter of direct observation. Let us now inquire into the relation between the small cyclonic vacillations of the weather and the type of climatic changes known as historic pulsations and glacial fluctuations. One of the most interesting results of recent investigations is the evidence that sunspot cycles on a small scale present almost the same phenomena as do historic pulsations and glacial fluctuations. For instance, when sunspots are numerous, storminess increases markedly in a belt near the northern border of the area of greatest storminess. That is, in southern Canada, and thence across the Atlantic to the North Sea and Scandinavia. See Figures 2 and 3. Corresponding with this is the fact that the evidence as to climatic pulsations in historic times indicates that regions along this path, for instance Greenland, the North Sea region and southern Scandinavia, were visited by especially frequent and severe storms at the climax of each pulsation. Moreover, the greatest accumulations of ice in the glacial period were on the poleward border of the general regions, where now the storms appear to increase most at times of solar activity. Figure 3a is displayed on the page. Figure 3. Relative rainfall at times of increasing and decreasing sunspots. Heavy shading, more rain with increased sunspots. Light shading, more rain with decreasing sunspots. No data for unshaded areas. Figures indicate percentages of the average rainfall by which the rainfall during periods of increasing spots exceed or fall short of rainfall during periods of decreasing spots. The excess or deficiency is stated in percentages of the average. Rainfall data from Walker, sunspots and rainfall. Figure 3b is displayed on the following page. Figure 3. Relative rainfall at times of increasing and decreasing sunspots. Heavy shading, more rain with increasing spots. Light shading, more rain with decreasing spots. No data for unshaded areas. Figures indicate percentages of the average rainfall by which the rainfall during periods of increasing spots exceeds or falls short of the rainfall during periods of decreasing spots. The excess or deficiency is stated in percentages of the average. Rainfall data from Walker, sunspots and rainfall. Even more clear is the evidence from other regions where storms increase at times of many sunspots. One such region includes the southwestern United States, while another is the Mediterranean region and the semi-arid or desert parts of Asia farther east. In these regions, innumerable ruins and other lines of evidence show that at the climax of each climatic pulsation, there was more storminess and rainfall than at present, just as there now is when the sun is most active. In still earlier times, while ice was accumulating farther north, the basins of these semi-arid regions were filled with lakes whose strands still remained to tell the tale of much increased rainfall and presumable storminess. If we go back still further in geological times to the Permian glaciation, the areas where ice accumulated most abundantly appear to be the regions where tropical hurricanes produced the greatest rainfall and the greatest lowering of temperature at times of many sunspots. From these and many other lines of evidence, it seems probable that historic pulsations and glacial fluctuations are nothing more than sunspot cycles on a large scale. It is one of the fundamental rules of science to reason from the known to the unknown, from the near to the far, from the present to the past. Hence it seems advisable to investigate whether any of the climatic phenomena of the past may have arisen from an intensification of the solar conditions which now appear to give rise to similar phenomena on a small scale. The rest of this chapter will be devoted to a resume of certain tentative conclusions which have no bearing on the main part of this book, but which apply to the closing chapters. There we shall inquire into the periodicity of the climatic phenomena of geological times, and shall ask whether there is any reason to suppose that the sun's activity has exhibited similar periodicity. This leads to an investigation of the possible causes of disturbances in the sun's atmosphere. It is generally assumed that sunspots, solar prominences, the bright clouds known as faculae, and other phenomena denoting a perturbed state of the solar atmosphere, are due to some cause within the sun. Yet the limitation of these phenomena, especially the sunspots, to restricted latitudes, as has been shown in Earth and Sun, does not seem to be in harmony with an internal solar origin, even though a banded arrangement may be normal for a rotating globe. The fairly regular periodicity of the sunspots seems equally out of harmony with an internal origin. Again, the solar atmosphere has two kinds of circulation. One, the so-called rice grains, and the other, the spots and their attendant phenomena. Now, the rice grains present the appearance that would be expected in an atmospheric circulation arising from the loss of heat by the outer part of a gaseous body like the Sun. For these reasons and others, numerous good thinkers from Wolf to Schuster have held that sunspots owe their periodicity to causes outside the Sun. The only possible cause seems to be the planets, acting either through gravitation, through forces of an electrical origin, or through some other agency. Various new investigations which are described in Earth and Sun support this conclusion. The chief difficulty in accepting it hitherto has been that although Jupiter, because of its size, would be expected to dominate the sunspot cycle, its period of 11.86 years has not been detected. The sunspot cycle has appeared to average 11.2 years in length, and has been called the 11-year cycle. Nevertheless, a new analysis of the sunspot data shows that when attention is concentrated upon the major maxima, which are least subject to retardation or acceleration by other causes, a periodicity closely approaching that of Jupiter is evident. Moreover, when the effects of Jupiter, Saturn, and the other planets are combined, they produce a highly variable curve which has an extraordinary resemblance to the sunspot curve. The method by which the planets influence the Sun's atmosphere is still open to question. It may be through tides, through the direct effect of gravitation, through electromagnetic forces, or in some other way. Whichever it may be, the result may perhaps be slight differences of atmospheric pressure upon the Sun. Such differences may set in motion slight whirling movements analogous to terrestrial storms, and these presumably gather momentum from the Sun's own energy. Since the planetary influences vary in strength because of the continuous change in the relative distances and positions of the planets, the Sun's atmosphere appears to be swayed by cyclonic disturbances of varying degrees of severity. The cyclonic disturbances known as sunspots have been proved by Hale to become more highly electrified as they increase in intensity. At the same time, hot gases presumably well up from the lower parts of the solar atmosphere and thereby cause the Sun to emit more heat. Thus, by one means or another, the Earth's atmosphere appears to be set in commotion and cycles of climate are inaugurated. If the preceding reasoning is correct, any disturbances of the solar atmosphere must have an effect upon the Earth's climate. If the disturbance were great enough and of the right nature, it might produce a glacial epoch. The planets are by no means the only bodies which act upon the Sun, for that body sustains a constantly changing relation to millions of other celestial bodies of all sizes up to the vast universes, and at all sorts of distances. If the Sun and another star should approach near enough to one another, it is certain that the solar atmosphere will be disturbed much more than at present. Here we must leave the cyclonic hypothesis of climate, and must refer the reader once more to Earth and Sun for fuller details. In the rest of this book we shall discuss the nature of the climatic changes of past times, and shall inquire into their relation to the various climatic hypotheses mentioned in the last two chapters. Then we shall inquire into the possibility that the solar system has ever been near enough to any of the stars to cause appreciable disturbances of the solar atmosphere. We shall complete our study by investigating the vexed question of why movements of the Earth's crust, such as the uplifting of continents and mountain chains, have generally occurred at the same time as great climatic fluctuations. This would not be so surprising were it not that the climatic phenomena appear to have consisted of highly complex cycles, while the uplift has been a relatively steady movement in one direction. We shall find some evidence that the solar disturbances which seem to cause climatic changes also have a relation to movements of the crust. End of Chapter 4. Section 5 of Climatic Changes, The Nature and Causes by Ellsworth Huntington. This LibriVox recording is in the public domain, recorded by Leon Harvey. Chapter 5. The Climate of History. We are now prepared to consider the climate of the past. The first period to claim attention is a few thousand years covered by written history. Strangely enough, the conditions during this time are known with less accuracy than are those of geological periods hundreds of times more remote. Yet if pronounced changes have occurred since the days of the ancient Babylonians, and since the last of the post-glacial stages, they are of great importance, not only because of their possible historic effects, but because they bridge the gap between the little variations of climate which are observable during a single lifetime and the great changes known as glacial epochs. Only by bridging the gap can we determine whether there is any genetic relation between the great changes and the small. A full discussion of the climate of historic times is not here advisable, for it has been considered in detail in numerous other publications. Our most profitable course would seem to be to consider first the general trend of opinion, and then to take up the chief objections to each of the main hypotheses. In the hot debate over this problem during the recent decades, the ideas of geographers seem to have gone through much the same metamorphosis as have those of geologists in regard to the climate of far earlier times. As every geologist well knows, at the dawn of geology people believed in climatic uniformity. That is, it was supposed that since the completion of an original creative act there has been no important changes. This view quickly disappeared and was superseded by the hypothesis of progressive cooling and drying, an hypothesis which had much to do with the development of the nebular hypothesis, and which has in turn been greatly strengthened by that hypothesis. The discovery of evidence of widespread continental glaciation, however, necessitated a modification of this view, and succeeding years have brought to light a constantly increasing number of glacial, or at least cool, periods distributed throughout almost the whole of geological time. Moreover, each year almost brings new evidence of the great complexity of glacial periods, epochs, and stages. Thus, for many decades, geologists have more and more been led to believe that in spite of surprising uniformity, when viewed in comparison with the cosmic possibilities, the climate of the past has been highly unstable from the viewpoint of organic evolution, and its changes have been of all degrees of intensity. Geographers have lately been debating the reality of historic changes of climate in the same way in which geologists debated the reality of glacial epochs and stages. Several hypotheses present themselves, but these may all be grouped under three headings, namely the hypothesis of 1. Progressive desiccation, 2. Climatic uniformity, and 3. Pulsations. The hypothesis of progressive desiccation has been widely advocated. In many of the drier portions of the world, especially between 30 degrees and 40 degrees from the equator, and preeminently in Western and Central Asia and in the southwestern United States, almost innumerable facts seem to indicate that 2,000 or 3,000 years ago the climate was distinctly moister than at present. The evidence includes old lake strands, the traces of desiccated springs, roads in places now too dry for caravans, other roads which make detours around dry lake beds, where no lake now exists, and fragments of dead forests extending over hundreds of square miles where trees cannot now grow for lack of water. Still stronger evidence is furnished by ancient ruins, hundreds of which are located in places which are now so dry that only the merest fraction of the former inhabitants could find water. The ruins of Palmyra, in the Syrian desert, showed that it must once have been a city like modern Damascus, with 100,000 or 200,000 inhabitants, but its water supply now suffices for only 1,000 or 2,000. All attempts to increase the water supply have had only a slight effect, and the water is notoriously sulphurous, whereas in the former days, when it was abundant, it was renowned for its excellence. Hundreds of pages might be devoted to describing similar ruins. Some of them are even more remarkable for their dryness than is Nia, a site in the Tarim Desert of Chinese Turkestan. Yet there, the evidence of desiccation within 2,000 years is so strong that even so careful and conservative a man as Han pronounces it überzeugend. A single quotation from scores that might be used will illustrate the conclusions of some of the most careful archaeologists. Among the regions which were once populous and highly civilized, but which are now desert and deserted, there are a few which were more closely connected with the beginnings of our own civilization than the desert parts of Syria and northern Arabia. It is only of recent years that the vast extent and great importance of this lost civilization has been fully recognized, and that attempts have been made to reduce the extent of the unexplored area and to discover how much of the territory, which has long been known as desert, was formerly habitable and inhabited. The results of the explorations of the last 20 years have been most astonishing in this regard. It has been found that practically all of the wide area lying between the coarse range of the eastern Mediterranean and the Euphrates, appearing upon the maps as the Syrian desert, an area embracing somewhat more than 20,000 square miles, was more thickly populated than any area of similar dimensions in England or in the United States is today, if one excludes the immediate vicinity of the large modern cities. It has also been discovered that an enormous desert tract lying to the east of Palestine, stretching eastward and southward into the country which we know as Arabia, was also a densely populated country. How far these settled regions extended in antiquity is still unknown, but the most distant explorations in these directions have failed to reach the end of ruins and other signs of former occupation. The traveller who has crossed the settled and more or less populous coast ranges of northern Syria and ascended into the narrow fertile valley of the Orontes, encounters in any farther journey towards the east an irregular range of limestone hills lying north and south and stretching to the northeast almost halfway to the Euphrates. These hills are about 2,500 feet high, rising in occasional peaks from 3,000 to 3,500 feet above sea level. They are grey and unrelieved by any visible vegetation. On ascending into the hills, the traveller is astonished to find at every turn remnants of the work of men's hands, paved roads, walls which divided fields, terraced walls of massive structure. Presently he comes upon a small deserted and partially ruined town composed of buildings large and small, constructed of beautifully wrought blocks of limestone, all rising out of the barren rock, which forms the ribs of the hills. If he mounts an eminence in the vicinity, he will be still further astonished to behold similar ruins lying in all directions. He may count 10 or 15 or 20, according to the commanding position of his lookout. From a distance it is often difficult to believe that these are not inhabited places, but a closer inspection reveals that the gentle hand of time or the rude touch of earthquake has been laid upon every building. Some of the towns are better preserved than others. Some buildings are quite perfect but for their wooden roofs which time has removed. Others stand in picturesque ruins, while others still are level with the ground. On a far-off hilltop stands the ruin of a pagan temple, and crowning some lofty ridge lie the ruins of a great Christian monastery. Mile after mile of this barren grey country may be traversed without encountering a single human being. Day after day may be spent in travelling from one ruined town to another without seeing any green thing save a terebinth tree or two standing among the ruins, which have sent their roots down into the earth, still preserved in the foundations of some ancient building. No soil is visible anywhere, except in a few pockets in the rock from which it could not be washed by the torrential rains of the wet season. Yet every ruin is surrounded with the remnants of presses for the making of oil and wine. Only one oasis has been discovered in these high plateaus. Passing eastward from this range of hills, one descends into a gently rolling country that stretches miles away towards the Euphrates. At the eastern foot of the hills, one finds oneself in a totally different country, at first quite fertile and dotted with frequent villages of flat-roofed houses. Here practically all the remains of ancient times have been destroyed through ages of building and rebuilding. Beyond this narrow fertile strip, the soil grows drier and more barren, until presently another kind of desert is reached, an undulating waste of dead soil. Few walls or towers or arches rise to break the monotony of the unbroken landscape, but the careful explorer will find on closer examination that this region was more thickly populated in antiquity even than the hill country to the west. Every unevenness of the surface marks the site of a town, some of them cities of considerable extent. We may draw certain very definite conclusions as to the former conditions of the country itself. There was soil upon the northern hills where none now exists, for the buildings now show unfinished foundation courses which were not intended to be seen. The soil in depressions without outlets is deeper than it formerly was. There are hundreds of olive and wine presses in localities where no tree or vine could now find footing, and there are hillsides with ruined terrace walls rising one above the other with no signs of earth near them. There was also a large natural water supply. In the north as well as in the south, we find the dry beds of rivers, streams, and brooks with sand and pebbles, and well-worn rocks, but no water in them from one year's end to the other. We find bridges over these dry streams and crudely made washing boards along their banks directly below deserted towns. Many of the bridges span the beds of streams that seldom or never have water in them, and give clear evidence of the great climatic changes that have taken place. There are wellheads and well houses, and inscriptions referring to springs, but neither wells nor springs exist today except in the rarest instances. Many of the houses had their rock-hewn cisterns, never large enough to have supplied water for more than a brief period, and corresponding to the cisterns which most of our recent forefathers had, which were for convenience rather than for dependence. Some of the towns in southern Syria were provided with large public reservoirs, but these are not large enough to have supplied water to their original populations. The high plateaus were of course without irrigation, but there are no signs, even in the lower flatter country, that irrigation was ever practiced, and canals for this purpose could not have completely disappeared. There were forests in the immediate vicinity, forests producing timbers of great length and thickness, for in the north and northeast practically all the buildings had wooden roofs, wooden intermediate floors, and other features of wood. Costly buildings such as temples and churches employed large wooden beams, but wood was used in much larger quantities in private dwellings, shops, stables, and barns. If wood had not been plentiful and cheap, which means grown nearby, the builders would have adopted the building methods of their neighbours in the south, who used very little wood and developed the most perfect type of lithic architecture the world has ever seen. And here there exists a strange anomaly. Northern Syria, where so much wood was employed in antiquity, is absolutely treeless now, while in the mountains of southern Syria, where wood must have been scarce in antiquity to have forced upon the inhabitants an almost exclusive use of stone, there are still groves of scrub oak and pine, and travellers of half a century ago reported large forests of chestnut trees. It is perfectly apparent that large parts of Syria once had soil and forests and springs and rivers, while it has none of these now, and that it had a much larger and better distributed rainfall in ancient times than it has now. Professor Butler's careful work is especially interesting because of its contrast to the loose statements of those who believe in climatic uniformity. So far as I am aware, no opponent of the hypothesis of climate changes has ever even attempted to show by careful statistical analysis that the ancient water supply of such ruins was no greater than that of the present. The most that has been done is to suggest that there may have been sources of water which are now unknown. Of course, this might be true in a single instance, but it could scarcely be the case in many hundreds or thousands of ruins. Although the arguments in favor of a change of climate during the last 2,000 years seem too strong to be ignored, their very strength seems to have been a source of error. A large number of people have jumped to the conclusion that the change which appears to have occurred in certain regions occurred everywhere, and that it is considered of a gradual desiccation. Many observers, quite as careful as those who believe in progressive desiccation, point to evidences of aridity in past times in the very regions where the others find proof of moisture. Lakes such as the Caspian Sea fell to such a low level that parts of their present floors were exposed and were used as sites for buildings whose ruins are still extant. Elsewhere, for instance, in the Tian Shan Mountains, irrigation ditches are found in places where irrigation never seems to be necessary at present. In Syria and North Africa during the early centuries of the Christian era, the Romans showed unparalleled activity in building great aqueducts and in watering land, which then apparently needed water almost as much as it does today. Evidence of this sort is abundant, and is as convincing as is the evidence of moister conditions in the past. It is admirably set forth, for example, in the comprehensive and ably written monograph of Leiter on the climate of North Africa. The evidence cited there and elsewhere has led many authors strongly to advocate the hypothesis of climatic uniformity. They have done exactly as have the advocates of progressive change, and have extended their conclusions over the whole world and over the whole of historic times. The hypothesis of climatic uniformity and of progressive change both seem to be based on reliable evidence. They may seem to be diametrically opposed to one another, but this is only when there is a failure to group the various lines of evidence according to their dates, and according to the type of climate at which they happen to be located. When the facts are properly grouped in both time and space, it appears that evidence of moisture conditions in the historic Mediterranean lands is found during certain periods, for instance 400 or 500 years before Christ, at the time of Christ, and 1000 AD. The other kind of evidence, on the contrary, culminates at other epochs such as about 1200 BC and the 7th and 13th centuries after Christ. It is also found during the interval from the culmination of a moist epoch to the culmination of a dry one, for at such times the climate was growing drier and the people were under stress. This was seemingly the case during the period from the 2nd to the 4th centuries of our era. North Africa and Syria must then have been distinctly better watered than at present, as appears from Butler's vivid description, but they were gradually becoming drier, and the natural effect on a vigorous, competent people like the Romans was to cause them to construct numerous engineering works to provide the necessary water. The considerations which have just been set forth have led to a third hypothesis, that of pository climatic changes. According to this, the Earth's climate is not stable, nor does it change uniformly in one direction. It appears to fluctuate back and forth not only in the little waves which we see from year to year or decade to decade, but in much larger waves, which take hundreds of years or even 1,000. These in turn seem to merge into and be imposed on the greater waves which form glacial stages, glacial epochs, and glacial periods. At the present time, there seems to be no way of determining whether the general tendency is toward aridity or toward glaciation. The 7th century of our era was apparently the driest time during the historic period, distinctly drier than the present, but the 13th century was almost equally dry, and the 12th or 13th before Christ may have been very dry. The best test of a hypothesis is actual measurements. In the case of the pository hypothesis, we are fortunately able to apply this test by means of trees. The growth of vegetation depends on many factors: soil, exposure, wind, sun, temperature, rain, and so forth. In a dry region, the most critical factor in determining how a tree's growth shall vary from year to year is the supply of moisture during the few months of most rapid growth. The work of Douglas and others has shown that in Arizona and California, the thickness of the annual rings affords a reliable indication of the amount of moisture available during the period of growth. This is especially true when the growth of several years is taken as a unit and is compared with the growth of a similar number of years before or after. When a long series of years is used, it is necessary to make corrections to eliminate the effect of age, but this can be done by mathematical methods of considerable accuracy. It is difficult to determine whether the climate at the beginning or the end of a tree's life was the same, but it is easily possible to determine whether there have been pulsations while the tree was making its growth. If a large number of trees from various parts of a given district all formed thick rings at a certain period and then formed thin ones for 100 years, after which the rings again become thick, we seem to be safe in concluding that the trees have lived through a long dry period. The full reasons for this belief and details as to the methods of estimating climate from tree growth are given in The Climatic Factor. The results set forth in that volume may be summarized as follows. During the years 1911 and 1912, under the auspices of the Carnegie Institution of Washington, measurements were made of the thickness of rings of growth from the stumps of about 450 Sequoia trees in California. These trees varied in age from 250 to nearly 3,250 years. The great majority were over 1,000 years of age, 79 were over 2,000 years, and 3 over 3,000. Even where only a few trees are available, the record is surprisingly reliable, except where occasional accidents occur. Where the number approximates 100, accidental variations are largely eliminated, and we may accept the record within considerable confidence. Accordingly, we may say that in California, we have a fairly accurate record of the climate for 2,000 years and an approximate record for 1,000 years more. The final results of the measurements of the California trees are shown in Figure 4, where the climatic variations for 3,000 years in California are indicated by the solid line. The high parts of the line indicate rainy conditions, the low parts dry. An examination of this curve shows that during 3,000 years, there have apparently been climatic variations more important than any which have taken place during the past century. In order to bring out the details more clearly, the more reliable part of the California curve from 100 BC to the present time has been reproduced in Figure 5. This is identical with the corresponding part of Figure 4, except that the vertical scale is 3 times as great. Figure 4 is displayed on the page. Changes of climate in California, solid line, and in Western and Central Asia, dotted line. Note, the curves of Figures 4 and 5 are reproduced as published in The Solar Hypothesis in 1914. Later work, however, has indicated that in the Asiatic curve, the dashed lines, which were tentatively inserted in 1914, are probably more nearly corrected than the dotted lines. Still further evidence indicates that the Asiatic curve is nearly like that of California in its main features. The curve of tree growth in California seems to be a true representation of the general features of climatic pulsations in the Mediterranean region. This conclusion was originally based on the resemblance between the solid line of Figure 4 representing tree growth and the dotted line representing changes of climate in the eastern Mediterranean region, as inferred from the study of ruins and of history before any work on this subject had been done in America. The dotted line is here reproduced for its historical significance as a stage in the study of climatic changes. If it were to be redrawn today on the basis of the knowledge acquired in the last 12 years, it would be much more like the tree curve. For example, the period of aridity suggested by the tip of the dotted line at about 300 AD was based largely on Professor Butler's data. As to the paucity of inscriptions and ruins dating from that period in Syria. In the recent article from which a long quotation has been given, he shows that later work proves that there is no such paucity. On the other hand, it has accentuated the marked and sudden decay in civilization and population which occurred shortly after 600 AD. He reached the same conclusion to which the present authors had come on wholly different grounds, namely that the dip in the dotted line about 300 AD is not warranted, whereas the dip about 630 AD is extremely important. In similar fashion, the work of Steen in Central Asia makes it clear that the contrast between the water supply about 200 BC and the preceding or following centuries was greater than was supposed on the basis of the scanty evidence available when the dotted line of Figure 4 was drawn in 1910. Figure 5 is displayed on the page. Changes in California climate for 2,000 years as measured by growth of Sequoia trees. Figure 5 is the same as the latter portion of Figure 4, except that the vertical scale has been magnified threefold. It seems probable that the dotted line at the right is more nearly corrected than the solid line. During the 30 years since the end of the curve, the general tendency appears in general to have been somewhat upward. Since the curve of the California trees is the only continuous and detailed record yet available for the climate of the last 3,000 years, it deserves most careful study. It is especially necessary to determine the degree of accuracy with which the growth of the trees represents 1. The local rainfall, and 2. The rainfall of remote regions such as Palestine. Perhaps the best way to determine these matters is the standard mathematical method of correlation coefficients. If two phenomena vary in perfect unison, as in the case of the turning of the wheels and the progress of an automobile when the brakes are not applied, the correlation coefficient is 1.00, being positive when the automobile goes forward and negative when it goes backward. If there is no relation between two phenomena, as is the case of the number of miles run by a given automobile each year and the number of chickens hatched in the same period, the coefficient is 0. A partial relationship where other factors enter into the matter is represented by a coefficient between 0 and 1, as in the case of the movement of the automobile and the consumption of gasoline. In this case, the relation is very obvious, but is modified by other factors, including the roughness and grade of the road, the amount of traffic, the number of stops, the skill of the driver, the condition and load of the automobile, and the state of the weather. Such partial relationships are the kind for which correlation coefficients are most useful, for the size of the coefficients shows the relative importance of the various factors. A correlation coefficient 4 times the probable error which can always be determined by a formula well known to mathematicians, is generally considered to afford evidence of some kind of relation between two phenomena. When the ratio between coefficient and error rises to 6, the relationship is regarded as strong. Few people would question that there is a correlation between tree growth and rainfall, especially in a climate with a long dry season like that of California. But the growth of the trees also depends on their position, the amount of shading, the temperature, insect pests, blights, the wind with its tendency to break the branches, and a number of other factors. Moreover, while rain commonly favors growth, great extremes are relatively less helpful than more moderate amounts. Again, the roots of a tree may tap such deep sources of water that neither drought nor excessive rain produces much effect for several years. Hence, comparing the growth of the huge Sequoias with the rainfall, we should expect a correlation coefficient high enough to be convincing, but decidedly below 1.00. Unfortunately, there is no need of the rainfall where the Sequoias grow, the nearest long record being that of Sacramento, nearly 200 miles to the northwest and close to a sea level instead of at an altitude of about 6,000 feet. Applying the method of correlation coefficients to the annual rainfall of Sacramento and the growth of the Sequoias from about 1863 to 1910, we obtain the results shown in Table 3. The trees of Section A of the table grew in moderately dry locations, although the soil was fairly deep, a condition which seems to be essential to Sequoias. In this case, as in all the others, the rainfall is reckoned from July to June, which practically means from October to May, since there is almost no summer rain. Thus the tree growth in 1861 is compared to the rainfall of the preceding rainy season, 1860 to 1861, or of several preceding rainy seasons, as the table indicates. Table 3 is displayed on the page, correlation coefficients between rainfall and growth of Sequoias in California. In the first line of Section A, a correlation coefficient of only minus 0.056, which is scarcely 6/10 of the probable error, means that there is no appreciable relation between the rainfall of a given season and the growth during the following spring and summer. The roots of the Sequoias probably penetrate so deeply that the rain and melted snow of the spring months do not sink down rapidly enough to influence the trees before the growing season comes to an end. The precipitation of two preceding seasons, however, has some effect on the trees, as appears in the second line of Section A, where the correlation coefficient is positive 0.288, or 3.2 times the probable error. When the rainfall of 3 seasons is taken into account, the coefficient rises to positive 0.570, or 8.7 times the probable error, while with 4 years of rainfall, the coefficient begins to fall off. Thus, the growth of these 18 Sequoias on relatively dry slopes appears to have depended chiefly on the rainfall of the second and third preceding rainy seasons. The growth in 1900, for example, depended largely on the rainfall in the rainy seasons of 1897 to 1898 and 1898 to 1899. Section B of the table shows that with 112 trees growing chiefly in moist depressions where the water supply is at a maximum, the correlation between growth and rainfall, positive 0.577 for 10 years rainfall, is even higher than with the dry trees. The seepage of the underground water is so slow that not until 4 years rainfall is taken into account is the correlation coefficient more than 4 times the probable error. When only the trees growing in moist locations are employed, the coefficient between tree growth and the rainfall for 10 years rises to the high figure of positive 0.605, or 9.8 times the probable error, as appears in Section C. These figures, as well as many others not here published, make it clear that the curve of Sequoia growth from 1861 to 1910 affords a fairly close indication of the rainfall at Sacramento, provided allowance be made for a delay of 3 to 10 years due to the fact that the moisture in the soil gradually seeps down the mountain sides and only reaches the Sequoias after a considerable interval. If a rainfall record were applied for the place where the trees actually grow, the relationship would probably be still closer. The records at Fresno, for example, bears out this conclusion so far as it goes, but as Fresno lies at a low altitude and its rainfall is of essentially the Sacramento type, its short record is of less value than that of Sacramento. The only rainfall records among the Sierras at high levels, where the rainfall and temperature are approximately like those of the Sequoia region, are found along the main line of the Southern Pacific Railroad. This runs from Oakland northeastward 70 miles across the open plain to Sacramento, then another 70 miles as the crow flies through Colfax and over a high pass in the Sierras at Summit. Next 20 miles or so down through Truckee to Boca, on the edge of the inland basin of Nevada, and on northeastward another 160 miles to Winnemucca, where it turns east toward Ogden and Salt Lake City. Section D of Table 3 shows the correlation coefficients between the rainfall along the railroad and the growth of the Sequoias. At Sacramento, which lies fairly open to winds from the Pacific and thus represents the general climate of Central California, the coefficient is nearly 5 times the probable error, thus indicating a real relation to Sequoia growth. Then among the foothills of the Sierra at Colfax, the coefficient drops till it is scarcely larger than the probable error. It rises rapidly, however, as one advances among the mountains, until at Boca it attains the high figure of positive 0.604, or 8 times the probable error, and continues high in the dry area farther east. In other words, the growth of the Sequoias is a good indication of the rainfall where the trees grow and in the dry region farther east. In order to determine the degree to which the Sequoia record represents the rainfall of other regions, let us select Jerusalem for comparison. The reasons for this selection are that Jerusalem furnishes the only available record that satisfies the following necessary conditions. 1. Its record is long enough to be important. 2. It is located fairly near the latitude of the Sequoias, 32 degrees north versus 37 degrees north. 3. It is located in a similar type of climate, with winter rains and a long dry summer. 4. It lies well above sea level, 2,500 feet, and somewhat back from the seacoast, thus approximating, although by no means duplicating, the condition of the Sequoias. And 5. It lies in a region where the evidence of climatic changes during historic times is strongest. The ideal place for comparison would be the valley in which grow the cedars of Lebanon. These trees resemble the Sequoias to an extraordinary degree, not only in their location, but in their great age. Some day it will be most interesting to compare the growth of these two famous groups of old trees. The correlation coefficients for the Sequoia growth and the rainfall of Jerusalem are given in Section A, Table 4. They are so high and so consistent that they scarcely leave room for doubt that where 100 or more Sequoias are employed, as in Figure 5, the curve of growth affords a good indication of the fluctuations of climate in Western Asia. The high coefficient for the 11 trees measured by Douglas suggests that where the number of trees falls as low as 10, as in the part of Figure 4, from 710 to 840 BC, the relation between tree growth and rainfall is still close, even when only 1 year's growth is considered. Where the unit is 10 years of growth, as in Figures 4 and 5, the accuracy of the tree curve is a measure of rainfall, is much greater than when a single year is used, as in Table 4. When the unit is raised to 30 years, as in the smoothed part of Figure 4, previous to 240 BC, even 4 trees, as from 960 to 1070, probably give a fair approximation to the general changes in rainfall, where a single tree prior to 1110 BC gives a rough indication. Table 4 is displayed on the page. Correlation coefficients between rainfall records in California and Jerusalem. Table 4 shows a peculiar feature of the fact that the correlations of Section A between tree growth and the rainfall of Jerusalem are decidedly higher than those between the rainfall in the two regions. Only at Sacramento and Boca are the rainfall coefficients high enough to be conclusive. This, however, is not surprising, for even between Sacramento and San Bernardino, only 400 miles apart, the correlation coefficient for the rainfall by 3-year periods is only 10.7 times the probable error, as appears in Section C of Table 4, while between San Bernardino and Winnemucca, 500 miles away, the corresponding figure drops to 2.8. It must be remembered that in some respects the growth of the Sequoias is a much better record of rainfall than are the records kept by man. The human record is based on the amount of water caught by a little gauge a few inches in diameter. Every gust of wind detracts from the accuracy of the record. A mile away, the rainfall may be double what it is at the gauge. Each zirconia, on the other hand, draws its moisture from an area thousands of times as large as a rain gauge. Moreover, the trees of which figures 4 and 5 are based were scattered over an area 50 miles long and several hundred square miles in extent. Hence they represent the summation of the rainfall over an area millions of times as large as that of a rain gauge. This fact and the large correlation coefficients between zirconia growth and Jerusalem rainfall should be considered in connection with the fact that all the coefficients between the rainfall of California and Nevada and that of Jerusalem are positive. If full records of the complete rainfall of California and Nevada on the one hand and of the eastern Mediterranean region on the other were available for a long period, they would probably agree closely. Just how widely the zirconias can be used as a measure of the climate of the past is not yet certain. In some regions, as will shortly be explained, the climatic changes seem to have been of an opposite character from those of California. In others, the Californian or Eastern Mediterranean type of change seems sometimes to prevail, but is not always evident. For example, at Malta, the rainfall today shows a distinct relation with that of Jerusalem and to the growth of the zirconias. But the correlation coefficient between the rainfall of 8-year periods at Naples a little farther north and of the growth of the zirconias at the end of the periods is negative 0.132, or only 1.4 times the probable error, and much too small to be significant. This is in harmony with the fact that although Naples has summer droughts, they are not so pronounced as in California and Palestine, and the prevalence of storms is much greater. Jerusalem receives only 8% of its rain in the 7 months from April to October, and Sacramento 13%, while Malta receives 31% and Naples 43%. Nevertheless, there is some evidence that in the past the climatic fluctuations of southern Italy followed nearly the same course as those of California and Palestine. This apparent discrepancy seems to be explained by our previous conclusion that changes of climate are due largely to a shifting of storm tracks. When sunspots are numerous, the storms which now prevail in northern Italy seem to be shifted southward and traverse the Mediterranean to Palestine, just as similar storms are shifted southward in the United States. This perhaps accounts for the agreement between the zirconia curve and the agricultural and social history of Rome from about 400 BC to 100 AD, as explained in World Power and Evolution. For our present purposes, however, the main point is that, since rainfall records have been kept, the fluctuations of climate, indicated by the growth of the zirconias, have agreed closely with fluctuations in the rainfall of the eastern Mediterranean region. Presumably the same was true in the past. In that case, the zirconia curve not only is a good indication of climatic changes or pulsations in regions of similar climate, but may serve as a guide to coincident but different changes in regions of other types. An enormous body of other evidence points to the same conclusion. It indicates that while the average climate of the present is drier than that of the past, in regions having the Mediterranean type of winter rains and summer droughts, there have been pronounced pulsations during historic times, so that at certain times there has actually been greater aridity than at present. This conclusion is so important that it seems advisable to examine the only important arguments that have been raised against it, especially against the idea that the general rainfall of the eastern Mediterranean was greater in the historic past than at present. The first objection is the unquestionable fact that droughts and famines have occurred at periods which seem, on other evidence, to have been moister than the present. This argument has been much used, but it seems to have little force. If the rainfall of a given region averages 30 inches and varies from 15 to 45, a famine will ensue if the rainfall drops for a few years to the lower limit and it does not rise much above 20 for a few years. If the climate of the place changes during the course of centuries so that the rainfall averages only 20 inches, the ranges from 7 to 35, famine will again ensue if the rainfall remains near 10 inches for a few years. The ravages of the first famine might be as bad as those of the second. They might even be worse, because when the rainfall is larger, the population is likely to be greater, and the distress due to scarcity of food would affect a larger number of people. Hence, historic records of famines and droughts do not indicate that the climate is either drier or moister than at present. They merely show that at the time in question the climate was drier than the normal for that particular period. A second objection is that deserts existed in the past, much as at present. This is not a real objection, however, for as we shall see more fully, some parts of the world suffer one kind of change and others quite the opposite. Moreover, deserts have always existed, and when we talk of a change in their climate, we merely mean that their boundaries have shifted. A concrete example of the mistaken use of ancient dryness as a proof of climatic uniformity is illustrated by the march of Alexander from India to Mesopotamia. Hayden gives an excellent presentation of the case in the second volume of his Overland to India. He shows conclusively that Alexander's army suffered terribly from lack of water and provisions. This certainly proves that the climate was dry, but it by no means indicates that there has been no change from the past to the present. We do not know whether Alexander's march took place during an especially dry or an especially wet year, in a desert region like Makran in southern Persia and Baluchistan, where the chief difficulties occurred. The rainfall varies greatly from year to year. We have no records from Makran, but the conditions there are closely similar to those of southern Arizona and New Mexico. In 1885 and 1905, the rainfall for 5 stations in that region was as follows. A table is displayed on the page. Mean rainfall during periods since observations began between 1885 and 1905. These stations are distributed over an area nearly 500 miles east and west. Manifestly, a traveller who spent the year 1885 in that region would have had much difficulty in finding water and forage than one who travelled in the same places in 1905. During 1885, the rainfall was 42% less than the average, and during 1905 it was 134% more than the average. Let us suppose, for the sake of argument, that the average rainfall of southern Persia is 6 inches today and was 10 inches in the days of Alexander. If the rainfall from year to year varied as much in the past in Persia as it does now in New Mexico and Arizona, the rainfall during an ancient dry year, corresponding in character to 1885, would have been about 5.75 inches. On the other hand, if we suppose that the rainfall then averaged less than at present, let us say 4 inches, a wet year corresponding to 1905 in the American deserts might have had a rainfall of about 10 inches. This being the case, it is clear that our estimate of what Alexander's march shows as to climate must depend largely on whether 325 BC was a wet year or a dry year. Inasmuch as we know nothing about this, we must fall back to the fact that a large army accomplished a journey in a place where today even a small caravan usually finds great difficulty in procuring forage and water. Moreover, elephants were taken 180 miles across what is now an almost waterless desert, and yet the old historians make no comment on such a feat which today would be practically impossible. These things seem more in harmony with the change of climate than with uniformity. Nevertheless, it is not safe to place much reliance on them except when they are taken in conjunction with other evidence, such as the numerous ruins, which show that Makran was once far more densely populated than now seems possible. Taken by itself, such incidents as Alexander's march cannot safely be used either as an argument for or against changes of climate. The third and strongest objection to any hypothesis of climatic changes during historic times is based on vegetation. The whole question is admirably set forth by J. W. Gregory, who gives not only his own results, but those of the ablest scholars who preceded him. His conclusions are important because they represent one of the few cases where a definite statistical attempt has been made to prove the exact condition of the climate of the past. After stating various less important reasons for believing that the climate of Palestine has not changed, he discusses vegetation. The following quotation indicates his line of thought. A sentence near the beginning is italicized in order to call attention to the importance which Gregory and others lay on this particular kind of evidence. Some more certain test is necessary than the general conclusions which can be based upon the historical and geographical evidence of the Bible. In the absence of rain gauge and thermometric records, the most precise test of climate is given by the vegetation, and fortunately the palm affords a very delicate test of the past climate of Palestine and the eastern Mediterranean. The date palm has 3 limits of growth which are determined by temperature, Thus it does not reach full maturity or produce ripe fruit of good quality below the mean annual temperature of 69 degrees Fahrenheit. The isothermal of 69 degrees crosses southern Algeria near Biskra. It touches the northern coasts of Cyrenaica near Derna and passes Egypt near the mouth of the Nile, and then bends northward along the coastlands of Palestine. To the north of this line, the date palm grows and produces fruit, which only ripens occasionally, and its quality deteriorates as the temperature falls below 69 degrees. Between the isotherms of 68 degrees and 64 degrees, limits which include northern Algeria, most of Sicily, Malta, and southern parts of Greece and northern Syria, the dates produced are so unripe that they are not edible. In the next cooler zone, north of the isotherm of 62 degrees, which enters Europe and southwestern Portugal, passes through Sardinia, and enters Italy near Naples, crosses northern Greece and Asia Minor to the east of Smyrna. The date palm is grown only for its foliage, since it does not fruit. Hence at Benghazi, on the North African coast, the date palm is fertile but produces fruit of poor quality. In Sicily and at Algiers, the fruit ripens occasionally, and at Rome and Nice, the palm is grown only as an ornamental tree. The date palm, therefore, affords a test of variations of mean annual temperature of 3 grades between 60 degrees and 69 degrees. This test shows that the mean annual temperature of Palestine has not altered since Old Testament times. The palm tree now grows dates on the coast of Palestine and the deep depression around the Dead Sea, but does not produce fruit on the highlands of Judea. Its distribution in ancient times, as far as we can judge from the Bible, was exactly the same. It grew at Jericho, the city of palm trees, Deuteronomy 34:3 and 2 Chronicles 28:15, and at En-Gedi, on the western shore of the Dead Sea, 2 Chronicles 20:2, Sirach 24:14. And though the palm does not still live at Jericho, the last apparently died in 1838, its disappearance must be due to neglect, for the only climatic change that would explain it would be an increase in cold or moisture. In olden times, the date palm certainly grew on the highlands of Palestine, but apparently never produced fruit there, for the Bible references to the palm are to its beauty and erect growth. The righteous shall flourish like the palm. Psalms 92:12. They are upright as a palm tree. Jeremiah 10:5. Thy stature is like to a palm tree. Canticles 7:7. It is used as a symbol of victory. Revelations 7:9, but never praised as a source of food. Dates are not once referenced to in the text of the Bible, but according to the marginal notes, the word translated honey in 2 Chronicles 31:5 may mean dates. It appears, therefore, that the date palm has essentially the same distribution in Palestine in the Old Testament times as it has now, and hence we may infer that the mean temperature was then the same as now. If the climate had been moister and cooler, the date could not have flourished at Jericho. If it had been warmer, the palms would have grown freely at higher levels, and Jericho would not have held its distinction as the city of palm trees. In the main, Gregory's conclusions seem to be well grounded, although even according to his data, a change of 2 degrees or 3 degrees in mean temperature would be perfectly feasible. It will be noticed, however, that they apply to temperature and not to rainfall. They merely prove that 2,000 years ago the mean temperature of Palestine and the neighbouring regions was not appreciably different from what it is today. This, however, is in no sense out of harmony with the hypothesis of climatic pulsations. Students of glaciation believe that during the last glacial epoch, the mean temperature of the Earth as a whole was only 5 degrees or 6 degrees Celsius lower than at present. If the difference between the climate of today and of the time of Christ is a tenth as great as the difference between the climate of today and that which prevailed at the culmination of the last glacial epoch, the change in 2,000 years has been of large dimensions. Yet this would require a raise of only half a degree centigrade in the mean temperature of Palestine. Manifestly, so slight a change would scarcely be detectable in the vegetation. The slightness of changes in mean temperature as compared with changes in rainfall may be judged from a comparison of wet and dry years in various regions. For example, at Berlin between 1866 and 1905, the 10 most rainy years had an average precipitation of 670 millimeters and a mean temperature of 9.15 degrees centigrade. On the other hand, the 10 years of least rainfall had an average of 483 millimeters and a mean temperature of 9.35 degrees. In other words, a difference of 137 millimeters, or 39% in rainfall, was accompanied by a difference of only 0.2 degrees centigrade in temperature. Such contrast between the variability of mean rainfall and mean temperature are observable not only when individual years are selected, but when much longer periods are taken. For instance, in the western Gulf region of the United States, the two inland stations of Vicksburg, Mississippi, and Shreveport, Louisiana, and the two maritime stations of New Orleans, Louisiana, and Galveston, Texas, lie at the margins of an area about 400 miles long. During the 10 years from 1875 to 1884, the rainfall averaged 59.4 inches, while during the 10 years from 1890 to 1899, it averaged only 42.4 inches. Even in a region so well watered as the Gulf states, such a change, 40% more in the first decade than in the second, is important, and in drier regions would have a great effect on habitability. Yet in spite of the magnitude of the changes, the mean temperature was not appreciably different, the average for the four stations being 67.36 degrees Fahrenheit during the more rainy decade and 66.94 degrees Fahrenheit during the less rainy decade, a difference of only 0.42 degrees Fahrenheit. It is worth noticing that in this case the wetter period was also the warmer, whereas in Berlin it was the cooler. This is probably because a large part of the moisture in the Gulf states is brought by winds having a southerly component. Similar relationships are apparent in other places. We select Jerusalem because we have been discussing Palestine. At the time of writing, the data available in the Quarterly Journal of the Palestine Exploration Fund cover the years from 1882 to 1899 and 1903 to 1909. Among these 25 years, the 13 which had most rain had an average of 34.1 inches and a temperature of 62.04 degrees Fahrenheit. The 12 with least rain had 24.4 inches and a temperature of 62.44 degrees. A difference of 40% in rainfall was accompanied by a difference of only 0.4 degrees Fahrenheit in temperature. The facts set forth in the preceding paragraphs seem to show that extensive changes in precipitation and storminess can take place without appreciable changes of mean temperature. If such changed conditions can persist for 10 years, as in one of our examples, there is no logical reason why they cannot persist for 100 or 1,000. The evidence of changes in climate during the historic period seems to suggest changes in precipitation much more than in temperature. Hence, the strongest of all the arguments against historic changes of climate seems to be of relatively little weight, and the pository hypothesis seems to be in accord with all the known facts. Before the true nature of climatic changes, whether historic or geologic, can be rightly understood, another point needs emphasis. When the pository hypothesis was first framed, it fell into the same error as the hypothesis of uniformity and of progressive change. That is, the assumption was made that the whole world is either growing drier or moister with each pulsation. A study of the ruins of Yucatan in 1912 and of Guatemala in 1913, as is explained in the climatic factor, has led to the conclusion that the climate of those regions has changed in the opposite way from the changes which appear to have taken place in the desert regions farther south. These Maya ruins in Central America are in many cases located in regions of such heavy rainfall, such dense forests, and such malignant fevers that habitation is now practically impossible. The land cannot be cultivated except in especially favoured places. The people are terribly weakened by disease and are among the lowest in Central America. Only 100 miles from the unhealthful forests we find healthful areas such as the coast of Yucatan and the plateau of Guatemala. Here the vast majority of the population is gathered and large towns are located, and the only progressive people are found. Nevertheless, in the past the region of the forests was the home of by far the most progressive people who are ever known to have lived in America previous to the days of Columbus. They alone brought to high perfection the art of sculpture. they were the only American people who invented the art of writing. It seems scarcely credible that such a people would have lived in the worst possible habitat when far more favoured regions were close at hand. Therefore it seems as if the climate of eastern Guatemala and Yucatan must have been relatively dry at some past time. The Maya chronology and traditions indicate that this was probably at the same time when moisture conditions apparently prevailed in the sub-arid or desert portions of the United States and Asia. Figure 3 shows that today, at times of many sunspots, there is a similar opposition between a tendency towards storminess and rain in subtropical regions and towards aridity in low latitudes near the heat equator. Thus, our final conclusion is that during historic times, there have been pulsatory changes of climate. These changes have been of the same type in regions having similar kinds of climate, but of different and sometimes opposite types in places having diverse climates. As to the cause of the pulsations, they cannot have been due to the precession of the equinoxes, nor apparently to any allied astronomical cause, for the time intervals are too short and too irregular. They cannot have been due to changes in the percentage of carbon dioxide in the atmosphere, for not even the strongest believers in the climatic efficiency of that gas hold that its amount could fluctuate in any such violent way as would be necessary to explain the pulsations shown in the California curve of tree growth. Volcanic activity seems more probable as at least a partial cause, and it would be worthwhile to investigate the matter more fully. Nevertheless, it can apparently be only a minor cause. In the first place, the main effect of a cloud of dust is to alter the temperature, but Gregory's summary of the palm and the vine shows that variations in temperature are apparently of very slight importance during historic times. Again, ruins on the bottom of enclosed salt lakes, old beaches now under the water, and signs of irrigation ditches where none are now needed, indicate a climate drier than the present. Volcanic dust, however, cannot account for such a condition. For at present the air seems to be practically free from such dust for long periods. Thus we now experience the greatest extreme which the volcanic hypothesis permits in one direction. But there have been greater extremes in the same direction. The thermal solar hypothesis is likewise unable to explain the observed phenomena, for neither it nor the volcanic hypothesis offers any explanation of why the climate varies in one way in Mediterranean climates and in an opposite way in regions near the heat equator. This leaves the cyclonic hypothesis. It seems to fit the facts, for variations of cyclonic storms cause some regions to be moister and others drier than usual. At the same time, the variations in temperature are slight and are apparently different in different regions, some places growing warm while others grow cool. In the next chapter, we shall study this matter more fully, for it can best be appreciated by examining the course of events in a specific century. End of section 5.